Yes class, in the previous video we have learned about the adjoint of the given matrix, and definitely the matrix will be a square matrix now. And in the next thing that we will discuss here under this exercise, there are two definitions. The first is singular matrix. Singular matrix. Now what is a singular matrix? It is a square matrix A is said to be singular, right? A square matrix A is said to be singular if determinant A is equal to 0. This is important. If the value of A determinant comes 0, what does it mean? The matrix is called a singular matrix. And the second definition is non-singular matrix. So it goes the other way. Non-singular matrix means a square matrix A is said to be non-singular if the determinant of A is non-zero, right? If determinant of A is non-zero, and definitely this A is a square matrix only. So if A is any square matrix and the determinant of A is not equal to 0, that means it can be negative number, it can come positive number, anything it is coming. But when we calculate the value of the A determinant, if it comes non-zero, then we say the matrix is non-singular, right? And based upon this, we have theorem 2. What the theorem 2 says, second theorem, the first theorem was based upon the adjoint, and the second theorem says if A and B are non-singular matrices, if A and B are non-singular matrices, non-singular matrices means the values of both the matrices, when I calculate the determinant of both the matrices is non-zero. So if A and B are non-singular matrices of same order, then AB and BA, AB and BA are also non-singular, right? Are also non-singular matrices of the same order. Definitely if I take A of order 2 and B of order 2 and both are non-singular, and when I take the product AB, then the AB will also be non-singular of the same order and BA also will be non-singular of the same order. Clear? So this is theorem number 2 based upon this. And the next result, that is very very important result, what is that? If this also can be considered as the theorem only. The theorem says that the determinant of the product of matrices is equal to the product of their respective determinants. This is the theorem, I think, let it be third theorem. If I take AB, means I am finding the product and then I am taking the determinant. So determinant of product of matrices is equal to product of their determinants. This is another important result based upon this. And definitely A and B will be the square matrices because we can find the determinant only of a square matrix, right? And the next theorem, that is, we have here, if we have the determinant of adjoint A, it will be equals to determinant A, and order will be here, that means the power will be here n minus 1, where A is a non-singular matrix, A is a non-singular matrix of order n. If this A is a non-singular matrix of order n, then what is the result we have? Then determinant of adjoint A, right? It will be equals to determinant A whole power n minus 1. And if I say A is a matrix of order 3, right? Then according to this result, I will get determinant of adjoint A. First I will find the adjoint of this matrix and then I calculate the determinant value of that adjoint. It will be equals to whatever A matrix was given, I calculate the determinant, and here the power will be 2, right? So this is very important result. Based upon this, 1 marker sums generally come. So the theorem is determinant of adjoint A, where the order of A is n, will be equals to determinant A power n minus 1, right? This is the next result. Okay, this was all about the definition of singular matrix. If determinant A value is coming 0, matrix is singular. If the value of A determinant is non-zero, the matrix will be called non-singular. And if A and B are non-singular matrices, their products also will be non-singular and of the same order. And the other important result that already mentioned here. And here the least thing, or means the most important thing of this exercise is, now I will say, a square matrix A is said to be singular, is said to be invertible. A square matrix A is said to be invertible if and only if A is a non-singular matrix. If and only if A is a non-singular matrix. So this is important definition, and based upon this we have the next result, how to find the inverse of the square matrix, right? Even in the exercise of matrices, where we have learned elementary operations to find the inverse of the matrix, there also whenever we find the inverse of the matrix was a square matrix, either of order 2 or order 3. So the next important way to find the inverse of the matrix is with the help of adjoint now. So first of all, if the matrix is invertible, we have to check first of all the value of the determinant. If the value of determinant is coming non-zero, it means the matrix is non-singular matrix. And after getting this, we will say the matrix is non-singular, so it is invertible. And if it is invertible, what is the formula to calculate the inverse? So A inverse will be equals to 1 upon value of determinant A into adjoint A. So this is the formula for the inverse of the matrix, 1 by determinant of A value into adjoint A. This adjoint A will be the matrix, this will be the number. So this number, if I divide with this adjoint A, that will be the inverse of matrix. So this is the important formula of this exercise, and based upon this we have sums in this exercise, as well as this formula we will use even in the solution of system of linear equations as well. That will be the next exercise, there we will discuss it. And first important formula it is, note down in your registers all the theorems, the results, the definitions you note down. And now we will see how to use this formula in calculating the inverse of the matrix, right? So let us do 1 or 2 sums based upon this method. So we will do here sum number 5 of exercise 4.5, right? We are taking sum number 5. We have to find the inverse of the given matrix if it exists. So whatever matrix is given, we will take, let A is equal to the matrix. So the matrix given is 2, -2, 4 and 3, right? One method we have done already, it is based upon elementary operations, and now we are doing with the help of adjoint method. And first of all, what we will find the determinant value. The determinant value will be here, this into this, minus -2 into 4. So 3 into 6 minus 4 into -2 -8, it is coming 14, not equal to 0. That is A is a non-singular matrix. A is a non-singular matrix, so A inverse exists. And what is the formula of A inverse? A inverse is 1 upon A determinant into adjoint of A. A determinant value is already calculated, it is 14, right? Adjoint A now we have to find, and I think in the previous video we have learned how to write down the adjoint of the matrix of order 2. These two elements, 1 position, 2 position elements will get interchanged. 3 will come here, 2 and here, and these two elements 1 position, 2 position, their signs will change. So minus 2 will become plus 2 and 4 will become minus 4. So this is the adjoint of the given matrix. So what will be the inverse then? 1 by 14 into adjoint, it is 3, then 2, then minus 4 and 2, right? So answer is done. This will be the inverse of the given matrix A. Similarly, you people will do the inverse of 3 by 3. There also we will find the determinant value. If it is non-zero, we will say A inverse exists. We will find the adjoint, and the formula, this formula we will apply, substitute there, and you are getting the answer. So you people can do here till sum number 11. Homework is this, till sum number 11 you people have to complete the exercise 4.5. The remaining topic we will discuss in the next class. Thank you, students.